Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over 3 worked examples to show you how to do problems involving phase and coherence. Now if you haven't already done so, check out my previous video covering the theory in this topic, and that way you can apply what you learned in that video to this one. So let's get started. Question 1 says, to investigate the interference of sound waves, a student connects a signal generator to 2 identical loudspeakers, as shown below. A microphone is used to detect the interference pattern. So here's your signal generator, loudspeaker 1 and loudspeaker 2, and we've then got a microphone connected to an oscilloscope where we can use the microphone and the wave pattern on the oscilloscope to detect the strength of the sound signal. Part A says the 2 sources of sound waves are said to be coherent. What does this mean? Well, remember from the theory video on phase and coherence, we can say that it means that the waves from the 2 sources have a constant phase relationship and therefore have the same frequency, wavelength and velocity or speed. Part B says loudspeaker 2 is now connected to a different signal generator which produces sound waves of a different frequency to those from loudspeaker 1. Are the 2 sources still coherent? Explain your answer. Well, our answer would be no, the waves from the 2 sources are no longer coherent. This is because the waves now have different frequencies. So we really need our 2 sources of sound waves or 2 loudspeakers to be connected to the same signal generator in order for the 2 waves to be coherent. If you have your second loudspeaker connected to a different signal generator from the first one, then chances are the 2 waves are not going to have the exact same frequency and therefore are not going to be coherent. Question 2 says plain water waves diffract through 2 slits in a barrier in a ripple tank. The diffracted waves overlap to produce an interference pattern as shown below. So here we've got plain water waves produced, and these are instant on a double slit, i.e. 2 gaps in this barrier, and we've got this interference pattern produced with the points labelled X, Y and Z. And part A says what is meant by diffraction. Well, this is a definition from the National 5 Waves topic, and you might remember that diffraction is the bending of waves through gaps or around obstacles. So in this case we've got the waves bending through the gaps. Part B says describe what is happening at point X. What type of interference is produced? Well, it's worth pointing out first of all that these straight line waves are called wave fronts and they also represent the crests of the waves. So that means that these curved waves are also the crests of our waves. So at point X, we've actually got this line overlapping with this line, which means we've got a crest meeting a crest. So that means we can say that crest meets crest at point X. And what type of interference is produced if we have a crest meeting a crest? Well, that is constructive interference. Part C says describe what is happening at point Y. What type of interference is produced? Well, looking back at the picture, point Y represents the point in between 2 crests, and that would represent a trough. So here we've technically got a trough meeting a trough, which again would be constructive interference. So if you imagine sort of invisible lines here overlapping that are exactly halfway between the 2 crests for this wave, then you could see that this sort of invisible line with this invisible line overlaps at point Y, so we get trough meets trough, which is also constructive interference. So we could say trough meets trough, and that's constructive interference again. Lastly, part D says describe what is happening at point Z. What type of interference is produced? Well, looking back at the picture, point Z is on the crest of this wave, which is also overlapping with the invisible trough of this wave. So we've technically got crest meets trough here, which is going to be destructive interference. And if it helps, you could draw sort of dashed lines in here halfway between the crests for both waves to show where the troughs are. So we can say for point Z, crest meets trough, and therefore that's destructive interference. Lastly, question 3 says 2 loudspeakers connected to the same signal generator emit the same note in phase. So you've got loudspeakers 1 and 2 here, both connected to the same signal generator, and we've then got points A to B labelled here. It says a girl covers her ear so that she only hears sound from her left and then walks from A to B. So the girl's walking from here to here listening to the sound. Part A says to describe what she hears. Well, as she walks from A to B, we would say that the girl hears alternate regions of loud and quiet sounds. Part B says relate this to constructive and destructive interference. So we want to think about loud and quiet in terms of constructive and destructive interference. So we could say the loud sounds are where constructive interference occurs and the quiet sounds are where destructive interference occurs. And this just comes from the definitions of constructive and destructive interference, because remember constructive interference involves 2 waves meeting exactly in phase where you get the crest meets crest and the trough meets trough, and that means you would get a wave of twice the amplitude produced, and therefore it's going to be a loud sound. Whereas for destructive interference, remember that's where we get 2 waves completely out of phase, where we've got the crest of one wave meeting the trough of the other wave, and that means we get complete cancelling out of the waves, i.e. a wave of 0 amplitude or 0 energy, and therefore that would be a quiet sound. Part C says describe what is meant by constructive interference in terms of the phase difference between two waves. Sketch a diagram to aid your description. Well, we could say that constructive interference occurs when the crest of one wave meets the crest of another, or the trough of one wave meets the trough of another, and the two waves are said to be in phase. The adding together of these two waves results in a stronger signal, one of twice the amplitude or twice the energy. And it would look something like this. So if you're overlapping one wave with another where the crest meets crest and trough meets trough, you'd get a wave of twice the amplitude. Part D then says describe what is meant by destructive interference in terms of the phase difference between two waves. Sketch a diagram to aid your description. Well, this time we can say destructive interference occurs when the crest of one wave meets the trough of another. The two waves are said to be out of phase, and the adding together of these two waves causes the signal to cancel out, i.e. we get a wave of zero amplitude or zero energy. And it looks like this. So if you were to overlap two coherent waves where you've got the crest of one meeting the trough of the other, then you get a wave of zero amplitude, or in a sense, no waves produced. And lastly, part E says where is the loudest point? Which type of interference is this? Well, if we look back at the picture, as the girl walks from A to B, she's going to hear alternate regions of loud and quiet sounds, as we said in part A, and remember the strongest signal is going to be detected exactly in the middle at a point of constructive interference. So we could say the loudest point is in the centre, halfway between A and B. This is a point of constructive interference, also known as a maximum. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.